Hello, I'm Mr. McBrien. This is TEJ20, Arduino 7, Sensors. Yesterday we talked about motors and functions that help us use them effectively. Today we're going to talk about sensors and talk about measuring distance. So, we've already alluded to sensors before when we talked about input pins for the Arduino. And we mentioned that there are many different kinds. There are fire sensors, heat sensors, water sensors, light sensors, and lots more. In fact, the sensor industry is a multi-billion-dollar industry. The one thing that we can keep in mind, the one thing that we need to realize defines a sensor, is that it converts a situation about which we're concerned into an electrical signal that we can use to infer something about the physical world. Now, as designers, it's our job to choose the right sensor, of course, for our situation, and then to write code that interprets the electrical signal in an intelligent way. And then, of course, uses that intelligence to make decisions. Let's talk for a second about what makes a good sensor. Of course, if I gave you the opportunity to talk about it, you'd talk about it, well, it should be cheap, it should be lightweight, it should be small, it should be tough, it should be waterproof, etc. All those things are true, and all those things apply to almost anything that you would want to own, right? Sensors, on the other hand, have a couple of requirements that are very specific to their situation. A good sensor will be sensitive to a given physical input within the ranges about which we care. But also, to be useful, this is the part that isn't quite so obvious, the sensor has to be insensitive to other inputs. So it has to be specific to the stimulus we care about. And of course, our test case here, our airport worker here, is illustrating that she wants to be able to see well. She wants to be sensitive to visible inputs while she's trying to exclude all of the auditory inputs, if we want to carry that metaphor along. Now, so to illustrate what happens when with a sensor that isn't insensitive to other inputs, we can imagine, for example, a light sensor that fails in low humidity. That's not very convenient, not very helpful. Now, having said that, there's no such thing as a perfect sensor. There's always limitations to every sensor. So what do we do when we have a sensor that isn't perfect? Well, the first answer would be enhance our design. So we might choose a different sensor. We might work hard to design something that can cope with whatever imperfectness we see in our sensor. And we're going to see an example of that later. Now, in cases where we can't fix what's wrong, we might design use cases where, let's take our example of a sensor that only works in low humidity. Well, we might actually require our given factory to have low humidity so that our system will work. So we put in dehumidifiers, for example. And if none of those things work, from a fun point of view, we might just decide to use that imperfectness in the sensor. For example, if we had an oxygen sensor that only works when it's not tilted, it only works when it's level, maybe it isn't a good oxygen sensor. Maybe to make a better tilt sensor for a robot. And there have been examples of these kinds of things where a sensor was designed and it was found that the stimulus they didn't want to measure was actually what it wound up being a sensor for. Okay, fun asides done. Let's talk about sound for a second. Sound waves are longitudinal vibration in air. You may have taken that in physics class. Solid objects will reflect those waves. and we call those things echoes. If we purposely generate a sound and then detect the reflection in order to locate an object in space, we call that echolocation. And echolocation has been used many times in air. Of course, bats taught us how to do that. In water, with a longitudinal vibration in water, whales use that to locate their prey. And we've designed systems to mimic those, of course. And that brings us to ultrasonic detection in the device at hand for today. We know that sound travels at 340 meters per second in air, give or take. If we know the time taken for a pulse to hit an object and reflect back to us, we can calculate the distance between us and that object. And this is how our ultrasonic detector works. So our first activity is to take and use the ultrasonic detector and wire that to the breadboard. Set up the code on the Arduino. The reference code is in the references for this talk. You can find it online. And output the distance to our serial monitor. And if you use the right equation, you can output it in centimeters. Go ahead and try that out. If you're using hardware, you can check the accuracy using a ruler. If you're not, if you're using Tinkercad, you can go ahead and just check to make sure that the code is working well. Now, outputting distance is sometimes interesting. However, of course, we're looking for the ability to make decisions based on that distance. So what I'd like you to do for your second activity is take your basic ultrasonic distance measuring device, add LEDs that evaluate the results and light according to how far away a given object is. Now, so that activity is a fun one. You shouldn't find it too challenging if you've been paying attention during your if-else lessons earlier. Let's have a little aside now and talk about a little bit more about that non-specificity. So when we have signal that's not associated with what we are trying to measure, we call this noise. So if our sensor were absolutely perfect, and it's not, we wouldn't see any noise. All we would see is, in the case of our distance measuring device, we'd see the perfect distance to the object. In fact, all sensors give some output, some electrical output that isn't associated with the target stimulus. There are two kinds. There's high frequency noise that's kind of random. So another way of looking at that is spikes. And then there's what we call low frequency noise. And that's generally associated with the baseline. It doesn't change very fast at all. And sometimes that'll be associated with things like temperature changes. Our ultrasonic detector is prone to random spikes in distance. So it'll measure distance perfectly, and suddenly it'll spike. And this kind of thing can cause incorrect results. If you imagine in a car, if you had a collision detection system that applied your brakes at full on, and your horn and an alarm and these kinds of things, and if every 1.3 seconds you had a random spike in noise, it would be a very exciting car ride, wouldn't it? So a very common problem in programming is eliminating those spikes, eliminating high frequency noise. And this can be removed mathematically by smoothing algorithms. it can also be removed logically. You can evaluate your signal. Now, in our case, remember that we're moving towards our summative project of a backup system for our car. Well, you could ask yourself, let's say for sake of argument that you're measuring the distance every 0.01 seconds. If the change in distance is 2 meters in 1/100th of a second, is that logical for a backing up car? Well, maybe with some of my friends driving, possibly. But normally I would argue that that's not a likely result. And that's more than likely a high frequency noise spike. So you can go ahead and do some reading on signal averaging as a noise correction technique, spike rejection, either one of those things. You can implement that inside your invention. And you will need to in order to get highest possible marks. I'd encourage you to get your device up and running. Observe it working. And after you've tested it, think about designing an algorithm to remove high frequency noise. Incidentally, this points out one of the awesome things about being a programmer. You often can fix things after hardware has been configured. Now, sometimes there's great problems associated with building your hardware and depending on the software team to fix all the problems with it. However, you can be quite effective if you know what you're doing and you plan ahead for this phase of software enhancement after the prototype device has been put in place. All right, so key points then. Ultrasonic detection is based on using the electrical output from a device, in this case, our standard ultrasound distance detector. Distance is an important, very interesting problem in robotics, and so it's interesting for us. Noise, though, is a common problem with almost all sensors. And this can be addressed often in software if it can't be addressed in device design. So for your homework, go ahead and keep refining that code. Don't forget your comments. Remember that this is going to be important for your final submission. And here's the reference for an ultrasonic detector, the one that we're using in class. Thanks very much. Have a great night.